Hey guys, it's the final video. I'm excited and you should be too. KSP time! What? You know what KSP stands for? Solubility product constant. It's like the constant for the dissociation of hydrogen. This is Ka, or anything with a K in front of it, some constant, okay? So here we got a little example of a dissolving thing at equilibrium, which is calcium fluoride. Dissolves into calcium and fluoride, but since it's equilibrium, it'll form as much as it'll dissolve. And then, so the solubility of calcium fluoride is dependent on the concentrations of calcium and fluoride, and not calcium fluoride itself, because that's a solid, and solids don't contribute to the solubility of a substance, because even though it's got an increased surface area, it forms just as quickly as it is dissolved, so even stirring or grinding up or anything like that won't increase the solubility of a substance. So let's do a problem. Let's talk about this problem. Copper IO3 goes to copper plus 2IO3. And the KSP is equal to the concentration of the copper and the IO3 squared, because there are two of them. And then the KSP value is already given for this problem here, which is 1.4 times 10 to the negative 7th. And we're trying to find the solubility of this CuIO3 at 25 degrees Celsius, so that's a standard temperature and pressure, 1 atm. And because we're trying to do that, we don't know the concentrations of these two at the moment. We'd like to. And because, so this one is represented by x because it's not squared, nor does it have any coefficients. This one represents 2x squared because it's squared here because of the coefficient, and we don't know how many moles it reacts at when it's dissolving, so we just put what is here down here as well. So that's why it is 2x squared. That's the easiest way for me to put it in my head. Usually I just remember that if it's got a number up here, just put it down here and here. And so you have to multiply those together and it gives you 4x cubed. To find x, just do a little bit of algebra here. Divide 1.4 times 10 to the negative 7th by 4, and then take the cube root of it, and you get x as 3.3 times 10 to the negative 3rd moles per liter, which equals your solubility. It's not really that hard of a concept to get. It's just a little tricky at first. Now we're going to talk about relative solubilities. Okay. Let's compare some solubilities. This is called relative solubilities. Now, anything with the largest KSP value will be the most soluble. That's just like food for thought. So here in this list, we've got 3 compounds that each have different solubilities, and I'm going to pull a Dora the Explorer and wait like 10 seconds and let you think for yourself which one has the largest solubility. And well, you know what? Just rank them in order. Do that. Ready? Ready? Go. Okay. Do you think I paused the video there? I didn't. I just stood still. Pretty impressive, right? You might think, oh, I'm really smart. this one has the smallest solubility, and this one has the largest solubility. No, you're wrong. You can't do that. This one has 5 ions. These two only have, well, okay. This one, this one has 6 ions. These two, or six elements in it. These two only have 5. Wow. Well, really, if you want to count these two. This one has 2, this one has 2, this one has 5. Well, no, 3. I can't count. Either way, they're different. And you can't compare ions with different numbers. Or you can't compare compounds with different numbers of elements in them, in compounds. It doesn't work that way. What you have to do is make sure that you have all the same ones. And if you run into this problem, yeah, you're not really that well off, actually. Yeah. You can't compare those. These two you can. This one definitely has the largest solubility, so if you want to make your life easy, just erase this one. That's all you have to do. This isn't a test or anything right here. And, there you go. This one's more soluble. Okay, we're good on that now. That wasn't that hard. Alright, let's talk about the common ion effect. Woohoo! What happens when a dissolved ion is in the same solution as the substance being dissolved? If that makes sense. So say we have solid silver chromate, I think, right here. And it is dissolving into silver and CrO4. But what if it's in a solution of water and silver nitrate? And the silver nitrate is already dissolved in the solution. It's in its separate ions of Ag and NO3. Whoa! This changes everything. Now instead of just doing 2x squared times x for our KSP value, we have to do 0.00 or 0.100 plus 2x squared for the Ag times just regular x because chromate isn't already in the water. Get what I'm saying? There's extra silver in there, and it's like the initial concentration of it. But because the KSP value for sodium chromate or silver chromate is so low at 9.0 times 10 to the negative 12th, we can get rid of the 2x on here just to make things simpler in life. So we can just do it as 0.001 or 0.100 squared times x equals 9.0 times 10 to the negative 12th. And we can find that the x value is like 9.0 times negative 10. So, or times 10 to the negative 10th. But either way, it's not really that hard. And the reason for this being that we have to add in this initial thing is that the ion is already present, and therefore it decreases the solubility of the ion. Yeah, so if Ag is already in the solution by itself, common sense, let's be honest here. If you've already got a partially saturated solution of something, it's not gonna dissolve more and more, especially if it's trying to go to an equilibrium with another substance. It's just gonna slow down the process of this one dissolving to maintain its already equilibrium. So, solubility is lower if the ion is already present in the solution. Yeah, that makes sense, sort of. Alright. I think we're moving on to our last thing, which is pH and solubility. Alright, pH and solubility. The pH of a solution greatly affects its solubility. In general, if there's a strong base and a weak acid, solubility will be increased. OH, like let's say we've got, I don't know why I wrote down this equation, I should have written down a different one. Let's say we've got OH on the right side here in the products, and if it's increased, well, okay, we've got an undissolved something over here with OH and an OH over here. If it's increased, the solubility will be decreased on this side, and therefore the formation again will be increased to compensate. But if H plus ions are added to this side, the solubility will increase because the OH will be lessened. I mean, that kind of makes sense, sort of. And so, in general, if it's something, if it's in an acidic solution, the solubility will be increased, but there must be an effective base there to compensate to speed up the solubility. Like silver chloride or sodium chloride, they will have pretty much the same solubility as in water, mainly because chloride is not an effective base at all. It's kind of weak, useless, so no HCl would be formed from that dissociation, and therefore the solubility will not be increased. So let me just write this down here. We got MgOH2 goes to Mg2 plus 2OH minus, right? So now we can visualize this a little bit. We got two OHs over here, which is your base and whatnot. I forgot to add an arrow there. And if the amount of OH, it's like an equilibrium expression. I mean, if the amount of OH is increased, the amount of OH over here will need to increase, and therefore the solubility will decrease because less is needed to dissolve into the new OH, and it needs to be going to formation over here. And what I said about H plus applies as well. So yeah, pH affects the solubility by far. Acidic reactions increase. Acidic solutions increase the solubility. Alright. Okay, summary time. What have we talked about? Solubility, KSP. What is KSP? It's the solubility product constant. What does that mean? Well, when something dissolves or is soluble, you can determine the rate of its solubility, and the constant, through KSP, which is usually just the concentrations of the products times each other, because most likely when something is soluble in water or something like that, it will be a solid, and solids do not contribute. They're useless. What else have we talked about? We determined solubility of something. That's not very hard. Relative solubilities. Something with a higher number in the KSP area will have a higher solubility than something with a lower number. But the only way to compare them is if they have the same number of ions present. Remember that. What else have we talked about? The common ion effect. If something has the same ions in the same solution, its solubility will be decreased. It's like an equilibrium expression, so we can hop on that train. We've all been there. And finally, we talked about pH and solubility. Something acidic, something dissolving in an acidic solution will have an increased solubility, and it needs a strong base from one of the dissolved particles in order for it to be effective and increase the solubility. Okay. Well, this has been the final video from Robert Schickling's chemistry videos. I hope you enjoyed. I know I have. Okay, Drew Thoughts time. Bye.
What about KSP?
KSP is my personal favorite, just because of how well I did on it. KSP is just it's a great thing.